morning, good afternoon, and good evening to everyone who joins us from around the world. This is Andrew and Renee. Welcome to the Stacks series.
It's wonderful to be here.
Today, we are exploring the bending of physics itself, specifically time crystals, time quasicrystals, and quantum spin liquids.
It is. I mean, it's a topic that sounds like it was ripped straight out of a science fiction novel, doesn't it?
It really does.
But what we're talking about today is very real. And it's really reshaping our fundamental understanding of matter.
Absolutely. When I first saw the stack of sources you sent over, I have to admit I checked the date to make sure it wasn't April Fool's.
I get that a lot.
We're talking about crystals, things I usually associate with engagement rings or salt shakers, but existing in time.
Exactly. It requires a complete shift in perspective.
Yeah.
A really fundamental one.
So let's set the stage a little bit before we get into the heavy quantum mechanics. We all think we know what a crystal is, in the traditional sense at least.
Right. You've got diamonds, you've got quartz, ice, table salt, things you can hold.
And what makes those things crystals? It's not just that they're hard or shiny, right?
No, not at all. It's all about their internal structure, the atoms inside. In a standard crystal, those atoms are arranged in a very specific, a very orderly repeating pattern in space.
On a lattice.
Precisely, a lattice.
Yeah.
If you could zoom all the way in on a grain of salt, you'd see sodium chloride, just repeating over and over and over again in 3 dimensions.
Okay, so they repeat patterns in space. That's the definition. The one we all learned in high school chemistry.
That's the one. And in physics, we have a fancier way of saying that. We say that a crystal breaks spatial translation symmetry.
Okay, let's unpack that. That sounds a little intimidating. Spatial translation symmetry.
It's simpler than it sounds, I promise. Imagine just empty space, total void. It's completely uniform. Every single point is exactly the same as every other point. If you move or translate 5 feet to your left, the laws of physics are the same, the space looks the same, nothing has changed. That's symmetry.
Got it. It's the sameness of empty space.
Yes, but the moment you put a crystal in that space, that symmetry is broken. It's gone. The space isn't uniform anymore. Now there are very specific spots where atoms sit and, empty spots where they don't. You've imposed a pattern, a grid.
Wait, so empty space is boring and predictable, but a crystal interrupts that. It breaks the sameness of space by adding structure.
You've got it. Now here is the central question of our whole discussion today. And it's the question that has kept physicists up at night for the last decade or so.
And that is?
What if a crystal could repeat its pattern, not in space, but in time?
So, just like a diamond repeats its carbon structure every few nanometers, you're saying a time crystal would repeat its own structure every few seconds, or microseconds.
That's the core idea. A repeating pattern, but the dimension it's repeating in is time itself.
And that is our mission for today. We're going to try and explain how physicists have apparently managed to break the laws of time translation symmetry.
And in doing so, created these states of matter that were, for a long time, thought to be completely impossible.
And we'll get into what this actually means for the future of things like, say, quantum computers. It's not just a curiosity.
Oh, not at all. And we're going to see how this whole journey took us from a really controversial theoretical dream to actual physical hardware running inside Google's quantum processors. It's an amazing story.
So let's go back to the beginning, the origin story. It all starts with a Nobel laureate, Frank Wilczek, back in 2012.
Yes. Frank Wilczek is he's a giant in the field of theoretical physics, a brilliant mind. The story goes that in 2012, he was teaching a class on ordinary crystals, space crystals.
Okay.
And he started thinking about the 4th dimension. In physics, especially since Einstein, we treat time as a dimension.
Right.
Space-time.
Right, they're woven together.
Exactly. So he just asked a very simple, almost childlike question. Mathematically, why should time be treated any differently than space when it comes to forming crystals?
It's a beautiful question. It's so simple. If nature loves symmetry and patterns, why limit crystals to just the 3 dimensions of space?
That was his thought process. So he proposed this new concept, a time crystal, and he defined it as a system that breaks time translation symmetry.
Okay, so just like the space crystal broke spatial symmetry, what does breaking time symmetry mean?
Well, normally we assume the fundamental laws of physics are constant over time. Energy is conserved. If you do an experiment right now, and then you do the exact same experiment 5 minutes from now, you expect the underlying conditions of the universe to be identical.
Sure, that makes sense.
That's time translation symmetry. Wilczek imagined a system that, even in its lowest possible energy state, what we call its ground state, would still exhibit periodic motion. It would change, and then return to its original state over and over, ticking like a clock forever without any energy input.
Okay, this is where it gets really, really weird, and also where my brain starts to hurt a little. You said lowest energy state.
I did, the ground state.
Usually, when things settle down to their lowest energy, they stop moving. That's the whole point.
That's our intuition. It's basic thermodynamics.
Right. If I drop a ball into a bowl, it rolls around for a bit, it loses energy to friction and sound, and eventually it settles right at the bottom. It stops. Ground state always equals stationary.
That is the intuition we all have. And that is precisely why Wilczek's proposal was so controversial, so explosive. He was suggesting you could have a system at the very, very bottom of the energy valley, the absolute ground state, that is still moving, still changing its configuration in a perfect loop.
It sounds like perpetual motion. And I'm pretty sure the patent office stopped accepting applications for those in, the 1800s?
It sounds exactly like it, and that was the immediate criticism. But there's a very subtle and very important difference. A perpetual motion machine, in the sci-fi sense, usually implies you can get free energy out of it. You can hook it up to a generator and power a city forever.
Right, that's the dream.
But Wilczek was very clear about this. His time crystal cannot do work. You cannot extract energy from it. If you tried to hook a tiny pulley to it or measure it in a way that drains energy, the motion would immediately stop. The crystal would melt.
So it's like a clock that has no battery and ticks forever, but the hands have zero weight, and you can't use them to power anything at all.
That is a perfect analogy. It moves, but it generates no entropy. It doesn't heat up. It just is. It exists in this perfect oscillating loop at zero temperature.
But the physics community didn't just accept this, right? I mean, I have to imagine people had major issues with the whole moving forever without energy input.
Oh, absolutely not. It sparked a massive, massive debate.
Right.
A lot of very smart people said it was simply impossible. And they had good reasons.
What were they?
Well, a couple of years later, two physicists, Haruki Watanabe and Masaki Yoshikawa, they came up with what's called a no-go theorem.
A no-go theorem. That sounds pretty definitive.
It was. They laid out a very rigorous mathematical proof that demonstrated that in any standard equilibrium system, so a system that's just left to itself, not being poked or prodded.
Like a rock on a table.
Exactly. In that kind of system, Wilczek's idea of a continuous time crystal is impossible. It simply cannot exist.
So the dream was dead just a few years after it was proposed.
For a moment, it really looked that way. They proved that if a system is in true thermal equilibrium, its ground state cannot depend on time. It has to be stationary. Full stop.
But clearly, the story didn't end there. This would be a very, very short discussion.
Correct. The definition had to evolve. Physicists are clever. If a rule says you can't do something, you look for a way around the rule. They realize, okay, if you can't make one in equilibrium, then you have to look at non-equilibrium systems.
You have to break the rules of the game.
You have to drive the system. You have to actively poke it.
And this brings us to the next chapter, making it real. The pivot from this continuous idea to something called a discrete time crystal.
This is where things get really exciting. And it's where we introduce the concept of a Floquet system.
Floquet sounds very elegant.
It's named after a French mathematician, Gaston Floquet. But in this context, it just refers to any system that is periodically driven.
So you're applying a force at regular intervals.
Exactly. Think about pushing a child on a swing. You're not giving one big push. You're giving small pushes at a regular rhythm. That's a driven system.
Okay. So instead of the rock just sitting on the table in equilibrium, we are now tapping the rock repeatedly with our finger.
That's the perfect way to think about it. And now let's use a better analogy to explain what a discrete time crystal, or a DTC, actually does. Let's think about a bowl of Jell-O.
I love Jell-O. This I can understand.
Great. So if you tap a bowl of Jell-O periodically, let's say you tap it gently once every second, what do you expect the Jell-O to do?
It's going to jiggle. It's going to wobble back and forth.
Okay, but at what frequency? At what rhythm?
Well, I assume if I'm tapping it once a second, it's going to jiggle once a second. It'll follow my lead. The jiggle will be synchronized with my tap.
Precisely. In almost any normal system you can think of, the response matches the drive. The Jell-O jiggles with the same period as your finger. But in a discrete time crystal, something utterly bizarre happens.
Okay, I'm ready.
You tap the Jell-O once every second, but it only jiggles once every 2 seconds.
Wait, so I tap it, it moves. I tap it again a second later, and it moves back to where it started.
Essentially, yes. You tap it, it goes, let's say, jiggle left. You tap it again a second later, it goes jiggle right back to the center. It takes 2 of your taps for the system to complete 1 full cycle and return to its original position.
So it's ignoring half of my instructions. It's running on its own schedule.
It has broken the symmetry of your driving force. You're giving it a rhythm with a period of t1 second, but the system adopts its own new rhythm with a period of 2t seconds.
So it has its own internal clock that's running at half the speed of the clock I'm trying to impose on it.
Exactly. This is called period doubling, and it's the key signature of a discrete time crystal. It has spontaneously broken the discrete time translation symmetry of the driver.
That is bizarre. It's like the Jell-O has developed a mind of its own. It's being stubborn.
It effectively does. And this suggests the material has a kind of rigidity, but not in space. It has rigidity in time. It resists the frequency of the driver and locks into its own preferred subharmonic frequency.
You mentioned rigidity. That's such a key word for normal crystals, right? A diamond is rigid in space. If I try to push one atom in a diamond, the entire lattice resists that push.
Yes, that's a fantastic connection. And the discrete time crystal is rigid in time. And this rigidity has a stunning consequence. It implies that if your tapping isn't perfect, maybe you get tired, you tap at 0.9 seconds one time, then 1.1 seconds the next.
Which would happen in the real world. Nothing is perfect.
Right. The crystal doesn't care. It filters out your noise. It keeps its own perfect, unwavering 2T rhythm. It effectively corrects your errors. This is what we mean by rigid long-range order in time.
That sounds incredibly useful. We'll definitely get to applications later, but I have a huge question right now.
Go for it.
If we're constantly driving this system, tapping the Jell-O over and over and over, aren't we just dumping energy into it? Wouldn't the Jell-O eventually just heat up and melt into a chaotic soup?
This is the million-dollar question. This is the central problem that had to be solved. And in any normal system, the answer is yes, absolutely. If you keep pumping energy into a quantum system with a laser, it heats up. The particles start moving around randomly. It becomes a featureless, chaotic hot soup. We call this thermalization.
And a thermalized soup cannot be an ordered crystal. It's the opposite.
Exactly. It would be like trying to build a skyscraper in a hurricane. The energy you're adding just destroys the order you're trying to create.
So how do you stop the Jell-O from melting? What's the secret ingredient?
The secret ingredient is a very strange quantum phenomenon called Many-Body Localization, or MBL.
Okay, another big term. Let's break this one down. Many-body localization.
Let's go back to an analogy. Imagine you have a perfectly clean, polished hardwood floor, a frictionless surface, and you spill a big bag of marbles onto it. What happens?
They go everywhere. They roll, they bounce off each other, they spread out until they cover the whole floor.
Right. They interact, they exchange energy, they mix. That's a perfect picture of thermalization. Energy spreads out rapidly through the whole system. Now, imagine a different floor. This one is an absolute mess. It's a teenager's bedroom. It's covered in junk books, shoes, clothes, maybe some sticky glue traps. It's a landscape of disorder.
Okay. A very messy floor. Now I spill the marbles.
What happens now? They don't go very far. One gets trapped behind a shoe. Another gets stuck in a pile of laundry. A third gets caught in the glue. They don't spread. They stay localized to the small area where they landed.
So adding disorder, making the system messy, actually stops the energy from spreading? That feels so counterintuitive.
It is deeply counterintuitive, but yes. In the quantum world, adding a strong random potential, the messy floor, prevents the particles from effectively communicating with each other. They can't exchange energy. They get localized.
So MBL is like a freezer mechanism for quantum systems.
That's a great way to put it. It prevents the system from absorbing any net energy from the laser pulses from the driving force. The energy goes in, but it can't spread around and heat things up, so it just gets stuck. It forces the system to remain in a specific quantum state.
So even though you're pounding it with energy, it doesn't heat up. It stays in this weird, protected, crypto-equilibrium state.
A state where it can oscillate forever without melting, yes.
That is fascinating. So to create this perfect new form of order in time, you first need to create a specific kind of mess in space.
It's a beautiful, beautiful irony of physics. You need disorder to protect the order.
So we have the theory, we have the Jell-O analogy, we have the messy floor. But does anyone actually build one of these things? Did it leave the blackboard?
Yes. The race to build the first one really, really heated up around 2016 and 2017. It was a very exciting time.
Who were the main players in that race?
We saw two major groups publish their results literally back-to-back in the same journal. It was clearly a tight race. One group was from the University of Maryland, led by Chris Monroe. They were using trapped ions.
Trapped ions, what are those?
They take individual atoms, in this case ytterbium atoms, and they strip an electron off to give them an electric charge. Then they can use electromagnetic fields to trap them, to make them levitate in a perfect line inside a vacuum chamber.
So they have a chain of hovering atoms. That's already cool.
It is. And then a different group at Harvard, led by Mikhail Lukin, took a completely different approach. They used something called nitrogen vacancy centers in diamonds.
Okay, what's a nitrogen vacancy center?
It's basically a tiny flaw in the diamond's crystal lattice. You have a spot where a nitrogen atom has replaced a carbon atom, right next to an empty spot of vacancy. And this specific type of flaw acts like a single controllable atom, a tiny magnet embedded in the solid diamond.
So one group used levitating atoms, the other used flaws in a diamond. And both saw this time crystal behavior.
They both saw the telltale signature, the period doubling. They would drive the system at one frequency and see it respond at half that frequency.
And there was another one, right, from Yale. I saw something in the notes about MAP crystals.
Yes, that one was a big surprise to everyone. The Yale group found signatures of time crystalline behavior in something called monoammonium phosphate.
That doesn't sound very exotic.
It's not. That's the stuff you find in those grow-your-own crystal kits you can buy for kids at a science museum.
Wait, you're telling me the stuff I grew in a beaker in 5th grade science class could be a time crystal?
It showed signatures. Now, it was a very different kind of system, but it suggested that this phenomenon might be far more common, more ubiquitous than anyone had previously thought. It might not require these incredibly exotic lab setups.
But there was a catch with these early experiments, wasn't there? They weren't perfect.
That's right. They were groundbreaking, but they were short-lived. In all these cases, the time crystal behavior, the oscillations, would eventually decay. They would melt after a fraction of the second or, few hundred cycles.
So they were like wobbly time crystals. They couldn't keep the rhythm forever.
You could call them that. They were incredibly compelling, but there were still debates in the community about whether they were true, infinitely stable time crystals or just very long-lived pre-thermal states that were just taking a very, very long time to melt.
So how do you prove it for good?
To really prove it, you needed a system where you could control everything perfectly. The interactions, the disorder, the drive. You needed a fully programmable quantum system.
Enter Google.
Enter Google.
This was in 2021, the Google Sycamore experiment. This really felt like the mic drop moment for the entire field.
It absolutely was. It was a landmark paper. They used their Sycamore quantum processor. Now, usually when we talk about quantum computers, we talk about them running algorithms to, factor huge numbers or simulate molecules.
Right, solving problems.
But here, they did something different. They didn't run code on the computer to simulate a time crystal. They used the quantum computer as the physical system itself.
Can you explain that distinction? That's really important.
Sure. Sycamore has, at the time, 53 functioning qubits. Qubits are the fundamental bits of a quantum computer. So Google's team took about 20 of those qubits, and instead of using them to represent ones and zeros for a calculation, they treated the qubits themselves as a physical chain of interacting magnetic spins.
Ah, so each qubit was one of the particles.
Exactly. And because it's a programmable computer, they could engineer the messy floor, the disorder we talked about, directly into the connections between the qubits. They could dial it in with perfect precision.
So they essentially built a synthetic piece of matter inside the chip, one that had the exact properties they needed.
A perfect controllable spin 12 chain with tunable disorder. Then they hit it with their version of the laser pulse, which was a specific repeating sequence of quantum gates, the operations that manipulate qubits.
And the result. Did the jello jiggle at 2T?
It worked beautifully, better than anyone expected. They observed what they called eigenstate order.
Which means?
It means that the system spins, you can think of them as pointing up or down flipped, in a perfect cycle that repeated exactly every 2 drive cycles. And crucially, because they had such fine control, they could verify that the system absorbed no net energy from the drive. It was stable, robust, and non-heating.
It checked all the boxes.
It checked all the boxes. And because it's a quantum computer, they could measure every single qubit individually and see what was going on.
And what did they see?
They saw what are called cat states.
Okay, here we go. We're in Schrodinger's cat territory now.
We are. The eigenstates, the stable, oscillating states of the crystal, weren't just simple patterns like up, down, up, down. They were quantum superpositions of macroscopically distinct states. Meaning the crystal was, in a sense, in a state of all spins up and all spins down at the same time. like the cat being both alive and dead.
Yeah.
This confirmed it wasn't just some weird classical pendulum effect. It was a true, deeply quantum phase of matter.
So Google's experiment essentially settled the debate. They proved that time crystals are a distinct, real phase of matter.
Correct. Just like we have liquid, solid, gas, and plasma, we now have time crystal on the list. It proved that matter is no longer just defined by how its atoms are arranged in space, but also by how they're arranged or patterned in time.
That is just mind-blowing. But of course, scientists are never satisfied. They achieve something impossible and immediately ask, what's next?
Always.
And that brings us to the next level of weirdness. Time quasicrystals.
If you thought time crystals were strange, time quasicrystals are another level entirely.
So let's start by defining quasicrystal in the normal spatial sense first. I've heard of Penrose tiles, for instance.
That's the perfect example. A normal crystal, as we said, has a simple repeating pattern, AB, AB, AB. A quasicrystal is different. It is perfectly ordered, but it never repeats.
Ordered, but not periodic. How does that work?
Penrose tiling is the famous example. You can tile an entire infinite floor using just two different shapes of rhombus, and the pattern you create follows very strict mathematical rules, but it never actually repeats the same arrangement twice. It's all order, no repetition.
And I remember reading that they have forbidden symmetries.
Exactly. In a normal repeating crystal, you can't have five-fold symmetry, like a pentagon. If you try to tile a floor with regular pentagons, you end up with gaps. It doesn't work. But quasicrystals can and do have five-fold rotational symmetry. It's one of their defining features.
So if we translate that to the time domain, a time quasicrystal would be a system that ticks, but the rhythm of the ticks never falls into a simple repeating pattern.
Precisely. It's a non-repeating rhythm. And this is explored just recently in a 2024 experiment from a collaboration between Washington University and Harvard.
What was the setup for that one?
They went back to the diamonds, those nitrogen vacancy centers, but instead of hitting the system with one consistent periodic pulse, like tap, 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 they hit it with a quasi-periodic drive.
And what does a quasi-periodic drive look like? Is it just random?
No, not random. That would just be noise. It's ordered, but non-repeating. They did it by using two different laser frequencies at the same time.
Okay.
But not just any two frequencies. They chose two frequencies whose ratio was the golden ratio.
Golden ratio. Fiber? Roughly 1.618, the number that shows up in seashells and galaxies.
That's the one. It's famous for being the most irrational number. What that means mathematically is that you cannot write it as a simple fraction. And this has a profound consequence. The two driving rhythms never perfectly line up. It's like having two drummers, one playing in a one-beat rhythm and the other in a 1.1618 beat rhythm. They will never hit the downbeat at the same time again.
So how does the crystal respond to this chaotic-sounding drumming? You'd think it would just turn into a mess.
You would. You'd expect it to just heat up and become noise. But it didn't. Incredibly, the system responded with a complex but ordered beating pattern.
Right.
It wasn't oscillating with a single period, but with a whole symphony of frequencies that were mathematical combinations of the two drive frequencies.
So it found a hidden harmony in the apparent chaos.
It found what's called hidden periodicity.
Okay, what does that mean?
There's a beautiful way to visualize this. Imagine you have a regular, perfect checkerboard grid in two dimensions. That's a normal 2D crystal. Now imagine you project that grid down onto a one-dimensional line. You shine a light from above and look at the shadow.
Okay.
If you project it at a weird, irrational angle, like the golden ratio, the pattern of light and dark spots on that 1D line will look ordered, but it will never repeat. It will be a quasi-crystal.
I see. The non-repeating pattern in 1D is actually just a shadow of a repeating pattern from a higher dimension.
That is exactly it. And that's what's happening with the time quasicrystal. Its rhythm looks non-repeating if you just look at it in our normal 1D flow of time. But mathematically, it behaves as if it's a regular periodic crystal that's oscillating in a higher dimensional time, and we're just seeing its shadow in our world.
So in a way, these crystals are dancing to a beat that exists in a dimension we can't perceive directly.
That is a poetic but surprisingly accurate way to put it. The true simple order exists, but you need to go to higher dimensional mathematics to see the full symmetry.
Wow, that's a lot to process. And this experiment showed that strong interactions between the spins provided the rigidity again.
Yes, and this was another key finding. They showed that even without the MBL messy floor that the Google experiment needed, the strong natural interactions between the spins and the diamond were enough to provide the rigidity, to lock the pattern in and prevent it from falling apart.
So it seems like interaction is the glue. It's the thing that holds these impossible states of matter together.
It is. Whether it's the localization from disorder or the rigidity from strong interactions, you need some mechanism to protect the delicate quantum state from the chaos of the outside world.
Okay, we've broken time symmetry. We've explored crystals that live in higher dimensions. Now let's shift gears a bit and talk about liquids. Specifically, a liquid magnet.
Quantum spin liquids, or QSLs.
Now, just to be clear, if I had a cup of quantum spin liquid, I couldn't drink it, right? It's not actually a liquid.
Definitely not. No, it's liquid only in the magnetic sense. It describes how the electron spins are behaving.
Okay, so explain that.
In a normal magnet, like the one on your refrigerator, the electron spins are highly ordered. In a ferromagnet, they all point the same way, all up. In an antiferromagnet, they alternate in a perfect pattern, up, down, up, down. They are frozen into a fixed, rigid pattern.
Like the atoms in ice, they're locked in place.
Exactly. Order equals solid or ice. Now, in a quantum spin liquid, the spins are highly entangled. They're all deeply connected to each other, but they never settle into a fixed pattern. They're constantly fluctuating, flipping, and changing, even if you cool the material down to absolute zero temperature.
So it's like the magnetic equivalent of water molecules that refuse to freeze no matter how cold it gets.
That's the perfect analogy. It is a state of perpetual dynamic quantum disorder.
Why do they refuse to settle down? Are they just rebellious quantum particles?
They are frustrated.
Relatable, I feel that.
It's a real term in physics, geometric frustration. And here's the classic analogy to understand it. Imagine you have three people, let's call them Alice, Bob, and Charlie, and they are standing at the corners of a triangle.
Okay.
And the only rule is you must disagree with your immediate neighbors. In magnetic terms, this is an antiferromagnetic interaction. Your spin wants to be opposite to your neighbor's spin.
Easy enough.
Okay. So Alice decides her spin is up. What does Bob have to be?
Bob has to be down to disagree with Alice.
Right. Alice is up, Bob is down. Now, what about Charlie?
Well, Charlie has to disagree with Bob, which means Charlie should be up. But Charlie also has to disagree with Alice, who is already up. So Charlie needs to be down. He can't be both.
Exactly. Charlie is frustrated. There is no configuration that can satisfy all the rules at the same time. The system has no single, stable, correct ground state. So it never settles. It constantly fluctuates between all the different possible compromises.
And if you have a whole material made up of a lattice of these interconnected triangles,
then the frustration spreads across the entire material. The spins can never lock into a simple up-down pattern. They remain in this dynamic, entangled, liquid-like state.
This only happens in specific materials with specific atomic arrangements, right?
Yes. We look for materials that have these triangular motifs built into their crystal structure. One famous example is a mineral called herbertsmithite, which has what's called a kagome lattice.
A kagome lattice.
It's a beautiful pattern of corner-sharing triangles. It looks like a traditional Japanese woven basket, which is where the name comes from. It's one of the most geometrically frustrated lattices known to exist.
And what makes these frustrated spin liquids so special? Why are physicists so obsessed with finding them?
It comes down to a property that sounds like science fiction: fractionalization.
Fractionalization. That sounds like splitting the atom all over again.
It's almost stranger than that. We all learned that electrons are fundamental elementary particles. You can't cut an electron in half. It has fundamental properties: a fixed mass, a fixed electric charge, and a property called spin.
Right.
But in the bizarre collective environment of a quantum spin liquid, the system as a whole behaves as if the electron is split apart. These fundamental properties get deconfined and can travel around separately.
What? So the properties of the electron just rip apart from each other?
In a collective sense, yes. You get the emergence of new quasi-particles. For instance, you can get spinions, which are particles that carry the electron's spin, but have no electric charge.
So it's like the ghost of the electron's spin just wandering through the material without its body, the charge.
That's a great way to think of it. And even more exotically, you can get things called anyons.
Anyons.
Yes. In the quantum world, all particles are either fermions, like electrons, or bosons, like photons. Anyons are a theoretical third category. They're neither. And they have an incredible property called braiding statistics.
Braiding, like braiding hair.
Exactly like that.
Yeah.
If you have two of these anyon quasi-particles in your material, and you take one and slowly move it in a complete circle around the other one, the quantum state of the entire system changes in a detectable way. It remembers the path that was taken. It's like you've tied a tiny, invisible knot in the fabric of the quantum wave function.
A knot. Knots are robust. They're hard to undo by accident. This sounds like it could be very useful.
Precisely. And that leads us directly to the idea of topological quantum computing, which we'll definitely get to in a minute. But first, we should talk about how we can merge these worlds, how we can use light to force normal materials into these exotic states.
Right, the next section. Photo-induced phases. So we can actually use lasers to temporarily turn a normal material into one of these quantum spin liquids.
That is the goal. And it's a field of research called Floquet engineering again. The same idea we saw with time crystals.
Using the hammer of light to sculpt the material's properties.
It's a very precise quantum hammer. The idea is to take a material called a Mott insulator, which is normally a fairly boring antiferromagnet, and pump it with a very specific kind of light.
And that is?
Circularly polarized light.
Circularly polarized. So the light wave is like corkscrewing as it travels.
Yes, exactly. It has a handedness, a chirality. It's either a right-handed or a left-handed corkscrew. And this property is crucial because it breaks time reversal symmetry.
Okay, let's unpack that one. Time reversal symmetry.
Most laws of physics look the same if you play the movie forwards or backwards. A planet orbiting a star looks fine in reverse. But a corkscrew moving forward looks very different from a corkscrew moving backward.
Yeah.
The handedness flips. So by shining this chiral light on the material, you're imparting a specific directionality, a handedness, to the behavior of the electrons.
And this is what creates a chiral spin liquid.
Yes. What the light does is it makes the electrons virtually hop between sites on the lattice. They don't actually move, but the light field encourages them to move in little loops around those frustrated triangles we talked about. This induces something called a scalar spin chirality. It basically twists the spins into a chiral liquid-like state.
So just for the duration that the light is hitting it, the material's magnetic properties transform into this exotic, frustrated liquid.
Correct. It's a non-equilibrium phase of matter that only exists because we are constantly driving it with the laser. We are essentially dressing the atoms in photons to fundamentally change their collective properties.
That is incredibly cool. We're not just discovering new materials that have these properties. We're actively synthesizing new phases of matter with basically a light switch.
It's like alchemy with lasers. We're transmuting the properties of matter on demand.
So this brings us to the big so what question. We've got crystals that tick in time, crystals that vibrate to the golden ratio, and magnetic liquids that tie themselves in quantum knots. Why should the listener care? Let's talk about the applications.
The biggest one, the one that gets the most attention and funding, is the holy grail of modern technology, building a useful quantum computer.
And the number one problem with quantum computers right now is that they are ridiculously fragile, right?
Extremely. The enemy is a process called decoherence. A qubit, the quantum bit, stores information in a delicate superposition. If that qubit gets jostled by a stray bit of heat, or a vibration, or a random magnetic field, it loses its quantum state. The data is destroyed.
It's like trying to balance a pencil perfectly on its tip during an earthquake.
That's a great analogy. It's an unstable state.
So how do time crystals help solve this problem?
Remember their defining property, rigidity. A discrete time crystal locks into its 2T rhythm, and crucially, it resists noise in the driving pulse. It's intrinsically stable against certain kinds of errors.
So if we encode our quantum data not in a single fragile qubit, but in the collective state of a time crystal,
it should be much more robust. It inherits the rigidity of the phase. The periodic ticking of the crystal can act like a form of natural built-in error correction. It's constantly resetting itself to the correct rhythm, averaging out the environmental bumps and wiggles.
So if you use a time crystal phase as a form of quantum memory, a qubit could potentially hold its state for orders of magnitude longer than a standard qubit can.
That's the hope. And the Google experiment showed early signs of this. The coherence of their qubits, how long they could hold their quantum state, was significantly longer when the system was operating in the time crystal phase compared to when it wasn't.
So instead of the quantum memory vanishing in a microsecond, it could last for seconds, maybe even minutes one day.
In the quantum computing world, that is an absolute eternity. It would be revolutionary.
And what about the quantum spin liquids, the knots? How do they help?
That leads to an even more radical idea called topological quantum computing. Remember the ennions and the braiding?
Tying knots in the quantum wave function, yes.
If you encode your information not in the state of a single particle, like spin up or spin down, but in the topology of these braids, in the knot itself, then the information becomes almost perfectly immune to local errors.
How so?
Think about a piece of string with a knot tied in the middle. If you just shake one little part of the string, the knot doesn't untie itself. A local jiggle doesn't change the global property of knottedness. To untie it, you have to perform a large global operation. You have to physically move the ends of the string.
So a common error, like a bit flip, which is just a local shake on one qubit, wouldn't corrupt the data at all.
Exactly. The computation becomes intrinsically fault-tolerant. The physics itself is the error correction. You wouldn't need to dedicate thousands of physical qubits to correct the errors on one logical qubit, which is the current, very inefficient approach.
That is a complete game changer. What about applications outside of computing?
Precision sensing is a big one.
Like building better clocks?
Potentially, yes. We use atomic clocks, which are based on the oscillation frequency of atoms for everything from GPS to synchronizing financial markets. They're incredibly precise. But a time crystal is arguably the most stable ticker that nature allows. It doesn't drift. Its frequency is locked and protected by the laws of quantum mechanics.
So we could have ultra-precise timekeeping, which would mean better GPS, better deep space navigation, better synchronization for global telecom networks.
And also magnetometry. Because these quantum states are so delicate and sensitive to their environment, you can turn that weakness into a strength. They are incredibly sensitive to tiny changes in their phase, which means they could detect minuscule magnetic or electric fields.
What would you use that for?
You could build sensors to map the tiny magnetic fields produced by the human brain with unprecedented resolution, or detect submarines, or find underground mineral deposits.
And there was a brief mention of energy storage in the notes. That sounds pretty far-fetched.
It is very futuristic, but the logic is there. Since a time crystal oscillates forever without losing energy to heat, without dissipation, it represents a kind of perfect, lossless energy storage system at the quantum level. If we could ever figure out how to couple to that motion without destroying it, we might be able to create systems that store energy in these oscillations. But that's a long, long way off.
And finally, let's just touch on the philosophical implications of all this.
This is what excites me the most, personally. For centuries, our entire conception of the phases of matter has been static. Solid, liquid, gas. They're defined by the spatial arrangement of atoms just sitting there.
Matter was a noun.
Matter was a noun. Time crystals prove that matter can also be a verb. Its fundamental identity, it can be dynamic.
We're finding phases of matter that don't just sit still, they dance.
A beautiful way to put it. We are rewriting the first chapter of the condensed matter physics textbook. We're discovering that there's this whole universe of non-equilibrium phases that only exist in time. Phases that are defined by their motion, not just their position.
It really feels like we're just scratching the surface of a whole new continent of physics.
We absolutely are. When you think about the timeline, from Wilczek's impossible dream in 2012 to the first shaky experiments in 2017 to Google's definitive proof on a chip in 2021, the pace of discovery is just breathtaking. We went from this violates the laws of physics to we can build one on demand in less than a decade.
Who knows what we'll find in the next decade?
Exactly. Maybe we'll find a time quasicrystal naturally occurring in the core of a neutron star, or use photo-induced spin liquids to finally build a room-temperature superconductor.
The possibilities seem endless once you stop just looking at the world in equilibrium and start, poking it to see what happens.
You start driving the universe, and you find it can do things you never imagined.
This has been an absolutely incredible journey. We've bent the rules of time, tied knots in quantum spins, and spent a lot of time tapping Jell-O.
All in a day's work for a physicist.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support. And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content, and support us on Patreon. Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.